Linear regression is one of the most widely used models in data science. But do you really understand its assumptions? There is one misconception about the linearity assumption that trips up beginners and even seasoned pros. In this video, we'll discuss the first assumption of the linear regression model, the linearity assumption. Stick around because by the end of this video, you'll have a better understanding of linear regression than 90% of the data scientists out there. If we Google assumptions of a linear regression model and click on the top three links, the first one is from Geeks for Geeks. The first assumption it states is that there should be a linear relationship between the predictors and the response variable. The second website is called Statistic Solutions and it also says the same thing. In fact, it even says that the relation should be in a straight line and not curvy linear. The third website is called Analytics Vidya and it also says the same thing, that the relationship between the dependent and the independent variable is linear. The first assumption of the linear regression model assumes linearity in parameters, which means the target variable y should be a linear combination of the estimates beta naught and beta 1 and not necessarily the independent variable x. All of this implies that this is a linear regression model. Even this is a linear regression model, and for that sake, any power to x is also a linear regression model. As long as the target variable is a linear combination of the parameters, it is a linear regression model. You can even have log x, sine square x, tan square x, or any function. I am repeating, as long as the target variable is a linear function of the parameters, it is a linear regression model. In fact, the top three cases here are a special kind of linear regression model called polynomial linear regressions. This naturally raises an important question. How does non-linear models look like? Here are a few examples of non-linear regression equations. In the first one, you can note that the target variable y is exponentially related to the parameter beta 1. In the second one, it's by a fraction, and in the third one, it's again exponentially related to beta 1. So all of these are not linear regression. Therefore, the first chart shows a typical linear regression model. But contrary to popular belief, the second chart is also of a linear regression model. In the next step, we'll walk the talk. We'll implement all of this in Python to have a deeper understanding of how does a linear regression model actually works. Suppose we are conducting an experiment to study the effects of drugs dosage on the relief experienced by the patient. The treatment group was divided into multiple subgroups and each of those subgroups received different amount of the drug. After a few hours, the patients were asked to report how relief they felt on a scale of 0 to 10. The y-axis represents the scale and the x-axis represents how much dosage the patient got. From the scatter plot, we can see that the patients receiving close to 0 mg of the drug reported no relief. And as the dosage amount increases, the relief reported by those patients also increase, but only up to a point around 1.5 to 2 mg of that drug. And as the amount of dosage increases beyond that, the reported relief decreases. Now let's say we want to model the relationship between the dosage and relief. The relationship is clearly not linear. But does that necessarily mean that we can't use a linear regression model? Let's see. We'll start by fitting a linear regression model as is. Let's invoke linear regression from scikit-learn, fit it on x and y, and let's predict for all the values of x. Now let's plot the data and our fitted line from this model. We can clearly see that the model is doing a pretty bad job. Now we can see that the relationship is kind of a polynomial. So now for all the values of the independent variable x, let's also compute x square and store both of these in a array called x transform. Invoke the linear regression model from scikit-learn again, fit it on x transformed and y, and now predict for all the values of x transformed. Now since we have two variables in this model, we'll have two coefficients. In this case, there are two coefficients, one is 12.6 and one is minus 4.1. The 12.6 is for x and minus 4.01 is for x square. Let's see how this model is doing. Let's plot the line and we can clearly see that this model does a pretty good job of understanding the relationship between x and y. And we can see that we have used x square in the model equation, and still we have only invoked the linear regression from scikit-learn. We have not used any fancy model. Let's look at the full equation of this model. Let's get the model intercept, coefficient of x and coefficient of x squared, and print the full equation of this model. So the full equation of this model is y is equal to minus 0.5 plus 12.7 into dosage minus 4.0 into dosage square. We can clearly see that the model is not really linear in dosage, but it is still a linear regression model. I hope after watching this video you see linear regression in a new light. You see that it's not really just fitting a straight line to the data, it's much more nuanced, much more complicated than that. If you have any questions, please drop in the comments. Thank you.